There are, I imagine, a lot of people in this room, I don't know exactly how many, I was thinking the majority, who would already get stumped by the word homological. So, okay, so I'm going to spend some time dwelling on that, and my apologies to the experts on this, who I know see a few here, for what I'm about to do to your beautiful field. This is the paper that I'm talking about by Malbos and Mimram, Homological Computations for Term Rewriting Systems, presented at FSCD last year in 2016. I want to point out FSCD is Formal Systems in Computation and Deduction. I'm actually leaving to go to the next one, co-located with ICFP tomorrow. And here's its steering committee. It was the first year. It was the merger of a term rewriting conference with the Lambda Calculus conference. On the steering committee, one of the folks who really helped make this merger happen was Chris Rose, who some of you may remember. He worked here at 2 Sigma, and then last year, very sadly, he died. He wasn't able to make it to the inaugural FSCD. And he's an expert in term rewriting. And he was, I didn't know him very well, but he was one of the people that convinced me that I should learn something about term rewriting, and it wasn't so distant from my interests as I thought. And the fact that there's an FSCD as a union of these conferences is in part his legacy. So I thought it would be appropriate to recognize him here at 2 Sigma today. All right, moving on. And a lot of you may know him from Debian as well. He was a devoted open source contributor and advocate. Okay, as I said, I think some of you know what term rewriting systems are, or at least you know enough of the words that you could hazard a pretty good guess. All right, so let's not talk about those. We'll come back to it. We'll come back to it. We'll come back to it. We're going to take a long journey, and I will ask that you bear with me as we do it. We're going to come to everything eventually in its own time. You remember these guys, the Platonic solids, and all the sides are the same, and pulled this from Wikipedia, right? And here they each have numbers of vertices, edges, and faces. And now you can do something here. Well, you can. Don't ask me how we came up with this. Well, I can take 4 and subtract 6 and add 4, and I get 2. Okay. I can take 8 and subtract 12 and add 6, and I get 2. Some folks noticed this fact some time ago and found it sort of interesting that it worked for the Platonic solids. And they said, well, gee, that must be one reason the Platonic solids are so special. And I'll point out as well that you'll see that the 8 and the 6 and the 6 and the 8 swap in those 2 as well. That's Poincare duality. We won't talk about that, but it's sort of neat. That one swaps with itself. So what does this have to do with homology theory? Sorry, there we go. That's what I have all my effects. I've got to replay them if I jump around too much. What does this have to do with homology theory? Well, I said, okay, so we can add some numbers to objects, right? We can look at objects and get some numbers out of them, spaces, shapes, and right? Interesting. And so homology theory is basically the practice or the habit of looking at spaces and figuring out how to get numbers from them that mean something with regards to those spaces and are what, in particular, people call invariants of them under certain sets of things. Just like under all the Platonic solids, that you always get 2 out there. So those shapes must have something to do with 2. But you know, often you don't just get integers out; you get these suckers called groups out. I imagine some more people know about groups in the audience, but I'm going to talk about them as well. So let's talk about them now. Here's groups sliced 6 ways. Right, so a group is a set with a single operation, a 0 element, and a negation operation, basically, and then the operation's associative. That's the theory of a group. You can also think of it as a generating set, and terms of this group, elements of this group, are just sequences of this set. Any arbitrary sequence, your generating set is ABC, ABBB, ACCA, and then you give relations such that ABC, you might say, equals D, or D plus E equals R plus Q or something, and then that sort of quotients, we say, by just taking that these 2 things are equal. And that's another way to present a group. Groups also, by Cayley, which some categorists may know as a special case of Yoneda, are a closed collection of permutations of a set. And you can think of them equivalently with that. Or if you can think of it as a category with one object. And we know categories have morphisms, and it's got a bunch of automorphisms, because where else can they go? There's only one object. But all of them are invertible. And that's a group. And they're also, topologically, given a space, they're all the closed paths in it. And all of these ways move between each other very easily. And why am I talking about all these ways is, in a sense, the pun of homology is precisely that you can think of groups algebraically and geometrically and topologically all at once, and combinatorially. And that, in some sense, explains to me by what we're talking about. You can then take all these perspectives on these things that are built, generalizing them and using them. One thing to note is that in almost all these versions of groups I've given, you have two groups that are the same but look different. For example, I can have a group with one element, like the trivial group or something, and then if I have another element, but I've quotiented it so that other element is equal to the first element, it's got more generators. It's different. I write it down. One uses two symbols, one uses one, but they're really the same thing. And just as one might look at two computer programs, right? You know, one that had a while loop and one that had a for loop, and you say they're the same program, right? For every, and in fact, maybe they even generate the same code if you've got a assembly, if you've got a smart enough compiler. But, they're obviously a different program. I wrote them down, they look different. I diff them, and they, I get a patch file out of it. So when we talk about groups, we really want to think of them as sort of the abstract structure with these different presentations. And the categorical version is nice because by the way you do things in category theory, there really is only the group. And the one reason you want to think about this, slow down? Sorry, okay. One reason you want to think about this fact is we want to ask what the rank of a group is. And the rank of a group is if you think of a group as a set, right? Just the set without any of the operations or laws, it's the cardinality of the set. But you need to pick the smallest possible cardinality of a set, because like I said, a group can have many presentations. And so one thing to ask about a group is how many elements does it have, but you can only ask that by considering the smallest way to present it, and which would be if you put it as a category, you count all the invertible morphisms, and it's how many there are. So homology theory, the slogan is a functor that goes from spaces to mathematical objects in a categorical sense. You have some category that's some space-like category. And I think of that as data structures that can represent spaces if you're a computer programmer, right? You're doing a 3D modeling software, and one software might represent things as meshes of triangles, and another piece of software might represent them as filled solids, and another one might be voxels. So you need to have some notion, be it voxels or filled solids of triangles, of how you're going to represent the space mathematically or in binary, if you prefer, and then you need to get numbers out of it. So here we've got 4 vertices, 6 edges, 4 faces. Another way you can look at the numbers is, well, there's one, quote, 0 blob, because there's this blah, the connected component. There's 0 1 blobs, which would be 2D components on any of these things, right? Because basically what you'd be looking for is something like a circle. And there really isn't, because any time I draw a circle on the face of one of these, I could always slide it around into a point. So there's no real place to put a circle here that's interesting. And there's 1 2 blob, because I can think of the whole thing. And if I wrapped a balloon around it, I couldn't pull that balloon down to a point. So those are some other numbers we can get out of it, depending on how you think about it. That formula I gave, by the way, V minus E plus F, is the subject, if you like, philosophy of math and science of this lovely book, Proofs and Refutations. It's really the classic in the modern philosophy of math. And it's sort of Platonic dialogues over many ways in which people could argue about what constituted an effective proof of Euler's formula, it's the starting point for modern philosophy of math. So that's one place. Tells you less about the math, but it's a great book. And you'll learn a lot of different proofs of this formula in there. Let me tell you that. Okay, so what we have is we really want to embark on a process of generalization. I showed you something very striking, that you get this Euler's constant out of all these things. And it turns out that you really don't even need Platonic solids. You can do it with anything that's sort of that structure, like the thing in the Proofs and Refutations. You can do it with that. It needs to be, in a sense, deformable into a sphere, in some sense. Pardon? What's the formula? That's the formula. The number of vertices minus the number of edges plus the number of faces. Equal in the case of a sphere to 2, or anything close to a sphere to 2. It might be equal to other things in other cases. It's called the Euler characteristic. For a torus, you get a different number. And we're getting there. You take that alternating sum, and you can imagine in higher dimensions, you have minus, plus, minus, plus. What if I had like a 4 space or a 5 space, and in imagine higher dimensions? Well, you can have those higher faces, and you can keep doing the formula with them. You take the alternating sum, or you might think of blobs and higher blobs. And now, what are Betti numbers? These blob numbers. And I'm not really telling you the real answer. It's a better answer to all of this. But you can think of them, in fact, as the number of holes at each dimension, or in another sense, the number of cuts you can make before you've cut the thing apart. Just as you could maybe cut a torus, and you can make one cut, but it's still a blob because you just unwind that, and then you've got to cut it again before you get 2 pieces. And the cuts are of different dimensionality. But you generalize that. Right? So you start with vertices faces, and then you get these more abstract things called Betti numbers. You start by saying the Betti numbers are really just how you can cut a thing up at dimensions. You say, no, they're actually the rank of the nth homology group. So, okay, what's that? Well, it's a group constructed from dissecting the object into n blobs and then finding the cycles that are the same cycles to each other. And looking at therefore, in the sense, the different sorts of ways of paths of different dimensionality through which you can navigate this object that are not the same and are not contractible to one another. But yeah, you can generalize further and say, okay, so what's a homology group? You have one for each n, but really what you want to talk about is all the n together, and then you stick them all together and you get functions between them that let you talk about how they relate to one another at all these dimensions. And that gives you the adjacent components of a chain complex. So let's, here's a chain complex. All right. Yeah, sorry. Maybe let's come back to that. I think we've gone about far enough in homology theory before maybe I need to explain why you care, if you're going to look at that. Yeah, okay. So, only the dankest memes. I put as much work into this as any other aspect of the talk. Friendship ended with homology. All right, there we go. Okay, so let's talk about rewrite systems. All right, let's rewind. We're not going to talk about all rewrite systems. We're just going to talk about very simple ones called string rewriting systems at first. And string rewriting system begins with the notion of a monoid. And I already told you what a group is. So a monoid is like a group, but without inversion. So it's much simpler. You set with a binary operation and a distinguished element so that you have an associative operation, and the element is the identity under that. And a lot of CS people are familiar with monoids for this point. Functional programming has... Oops, sorry, I'm going to have to go through this gag again. There we go. That's what I wanted. So here's some simple monoids we're all familiar with. A lot of these instances are in the Haskell-based libraries. So the set true, false under the operation and false is the identity, right? What does that? Maybe true, huh? True is the identity. I'm sorry, yes. I inverted these two. Under the operation and true is the identity, because anything in true is the same thing, and anything in, or false is the same thing. So, all right, or the natural numbers under addition, or the natural numbers under multiplication, right? And in one case, 0 is the identity, in one case, it's 1. These are familiar monoids. You can have some really weird monoids. There's a whole branch of math that finds really fascinating ones. Just like with groups, to talk about them, they feel a bit inaccessible, because you can write finite monoids just by their multiplication tables, right? But you want to write richer ones. So you look at presentations just like with groups. So you can have potentially infinite monoids with more elements than you could possibly manually write out all the combinations of how the operation acts on them. But you want to give a very small presentation that says what this infinite thing is. And just like with groups, all monoids are the quotients of free monoids, which is to say, given any weird, crazy monoid you can come up with infinite elements or whatever, you can take a monoid and present it as a set, and then you have a pair where you have words from this set, which are sequences, strings. So The free monoid, as we're familiar with, is often we call the list, right? So a free monoid over some set ABC is just strings in ABC. Because, and we won't go into why we call it that, actually. I'd like to, but that's another talk. And examples are, again, so we can write and I left out the second piece of that, which is the quotienting. So if you just take things generated by one element A, under no other laws, that gives you the natural numbers, right? A, right? 1, 2, 3, 4. You just count how many A's you have, right? Just like you're counting apples in first grade. If you pick it under the law so that if you have A twice, that's the same as A once, that gives you the Boolean lattice in a sense. That gives you true and false, because either you've seen one A or you've never seen an A, and those are true and false. And that works out. You can convince yourself that that's a presentation of the bools. PQ such that PQ equals 1 is called the bicyclic monoid, because you can have sequences of P's or sequences, yeah? It can be either. They're equivalent, right? It just depends on how you assign what, right? The and the or are the same one, in fact, right? They're dual, so it doesn't matter. P and Q, you get this thing called the bicyclic monoid. I forget exactly how it works, but it's a good example of a slightly interesting one. You can't ever have a P followed by a Q is sort of what happens here. And otherwise you can have anything. But so once you have a P, then you're never going to see any more Qs after that. Then you have the free band on two elements, and you get a band whenever you have those, if everything squared is itself, then you call that a band, and that means that you can have sequences of A's and, or you can have, you can have A's and B's, but you can never have two A's in a row or two B's in a row. So, these are all interesting structures, and the interesting thing is they all obey the monoid laws, and you can convince yourself of this. And you can do really rich things with them. And these things actually are related to computer science, but we'll get to there. Why. So all presentations give rise to monoids. Monoids each admit multiple presentations, as we talked about. So example, the Boolean lattice, you could pick either for true and false, and it works. Slow down, thank you, Eve. That's why I asked for, I get fast, and I need the help. So monoid presentations, people realized, are exactly the same things as string rewriting systems. There's no difference at all. They're undirected string rewriting systems. But so you have a famous problem that actually came up related to computer science called the word problem, which is given a monoid presentation, find an algorithm to test if any two elements are equal under the given rewrite rules. And I'm going to give you a short proof that, I showed you how to give these things, and you might think, okay, I know how to test for equality, is you just write these things down and you apply the relations and see if they come out the same. But remember, some relations can make something bigger and others can make it smaller again. And maybe if you make it bigger and then smaller, you don't come back to where you started, depending on the path you took, right? So it's not so simple. And let me give you an example that's a very computer sciencey one. And this is a post. This is not, there's a different post problem, but this is the one of interest to us. And it's nicer, I think. Consider a monoid presented by three terms named S, K, and I. Equip to them the laws of the combinators S, K, and I. And then look up the halting problem in Wikipedia. Right? We've just embedded a Turing machine inside a string rewrite system. So if you could solve the word problem for all monoids, you could solve the halting problem. So this gave a very nice, very hands-on, simple to explain undecidability result, right? Here's something fundamentally mathematically undecidable, but it's really just about asking if two words look like each other. It's not about any machines or anything. So string rewriting has a long history in computer science. Some of the places that we tend to see it, as I pointed out, fundamental results in computability. When you think about instruction sequences in assembly, what are they? There's strings of assembly instructions, and some are like others and some aren't. And optimizers take one string and turn it into another string that does the same thing. Sometimes they even do it in the middle of the processor. Superscalar stuff. Unrestricted grammars, if you're interested in grammars in that computer science sense. Combinatory logic, as I pointed out, are all instances of, yes? So S, K, and I are famously three combinators by which you can produce a combinatory logic of sequences of S, K, and I and reduction rules are equivalent to Turing machines. I can't go more into it, but that's where that's going. Is they're a way to present Turing machines through what's called a combinatory logic. Operational transformation, which you really think of as when you have Google Docs and you have 4 people typing at once and they're all editing. How does it keep it in sync? Well, it's got to be able to know that some operations commute with others. So if I type this over here and Joe typed that over there, that's fine. And others don't, and they need some sort of sequencing. And that's the general way to look at that is called operational transformation. And you can think of that as linearized sequences of, of actions that happen in the world. In distributed and asynchronous systems, right, exactly questions like the word problem and so on have to do with CRDTs. Right? You have strings of information coming in, sequences of actions people are taking with regards to some distributed data structure. And you want to be able to find minimal representations of what that is. And you want to even know if that gives you a single answer at the end of the day, or if maybe you have some weird loop in there. So very common and very rich set of applications that are hopefully of interest to this audience. Another computer science fellow here, Knuth. And Knuth-Bendix were working, I believe this was initially motivated by computer algebra. And they considered, actually for theories, but we're going to do just monoids. You start with a finitely presented monoid, which is a monoid which has a finite set of generators and a finite set of relations, right? So you've got to be able to type it into the computer. And you can create what's called a confluent normalizing directed rewrite system, which is a different presentation of the same thing. But it's a presentation such that it always terminates, that every rewrite rule only gets applied in one direction, and you just keep applying them over and over, and you always come down to what's called a normal form, just like when we put terms into normal form in the lambda calculus or in a logic. And then, since every term uniquely rewrites to a normal form, you solve the word problem by rewriting terms to their normal form and then comparing for equality directly. And we do that by systematically rewriting the rewrite rules into different rewrite rules that still work to give the same monoid. Yes?
That's a violation of type. You can't rewrite. Right?
Yes, Jay, yes.
Sorry.
Yes, this is a higher rewriting presentation. That's a good point, actually. He's pointing out something interesting happens. And Knuth-Bendix obviously couldn't work always, otherwise it could solve the halting problem. But when it doesn't work, it fails to terminate. So that's good. The universe is safe. Newman's lemma, by the way, says that if all critical pairs are confluent in a rewrite system, then the entire system is globally confluent. Confluent meaning it always comes to the same answer. And we're going to get to what that is. A critical pair is when you have a branch such that you can go 2 different ways and choose to apply 2 different rules. And you might come to different places. And then confluence means that you can take those 2 places you've come to, and then there's another 2 rewrite rules that will eventually take you back to the same place anyway. So as the great Yogi Berra said, when you come to a fork in the road, you can take it. That's confluence. Here's an example I took from Wikipedia of, here's a presentation of a monoid. I don't know, this is just one. I don't know which one it is. It's the Wikipedia example monoid. That's its name. You can create directed reductions from this, right? They start with equalities. So you pick a lexicographic order so that it just gets smaller by some ordering on the strings as you go down across. And now you check for overlaps and you find critical pairs. And that's how you find them, is you say, okay, I have 2 rules, and the end of one shares the beginning of another. So if I have a term that ends with one thing, and then another term but then it starts with the beginning of the next thing, then I could, in that middle bit, apply either rule. So how do I know which rule to apply? Well, that's the critical pair, is given those 2, I could apply 2 different reductions and get 2 different answers. But Knuth-Bendix says, well, since we know that we started with a system that worked, we know that there's got to be a rule to complete that pair. And we add that new rule by then equating the 2 things that came out of the 2 branches of the critical pair and just writing from the bigger one to the smaller one. And so all your rules keep making things smaller, which is how you know it terminates. And every time you have a critical pair, you just close it up by rewriting to the smaller. Now, there might be some rules made redundant by this. You delete them, and then you go back to step 2, and you keep doing it, and eventually you get to that result at the bottom, in this case. So that's our example of Knuth-Bendix. So we said it doesn't always terminate. But what if we know that we can solve the word problem? What if we have a solution to the word problem already? Can we come up with a rewrite system that gets us that solution? So can we always solve the word problem by normalization if we can solve it at all? That's a good question. This right here is, I believe it's called Artin's presentation of the two braid. That ST such that STS equals TST. Yeah. No normalization of this is possible. However, it has a decidable, it's decidable word problem. And here's how I think about it. Now, you can see sort of why you can't really normalize it, right? Because, you know, anytime imagine just a long sequence of alternating S's and T's, you could just keep flipping them over and over and you wouldn't know when you were done in any local sense. But there's a global sense in which you could know you were done. Is you say, my normal forms must always start with S. And then if they always start with S, you've pinned down one side, and then everything else has to follow. But you can't say starts with in this presentation. There's no notion of a beginning. And you've had this when you write regex, and you must sometimes use the $sign in the regex, right? That's what you don't have a $sign in this. But the answer is you can create a new presentation of the same monoid, but that has more generators. And one generator, A equals ST for the start, and that's your $sign. And now that one does have a normalizing confluent system. So there are word problems that are decidable, but that Knuth-Bendix can't take us to. And the question is, well, there's a lot of questions that come from here. The question remains, is there any other way to get to them if not Knuth-Bendix? That's just an algorithm. It doesn't claim to be the answer for everything. It just says when it works, it's great, and when it doesn't work, well, you can keep waiting and maybe it'll work. Right? It just doesn't terminate. When it doesn't work, you don't know. So we have to establish as a question over all possible generators, not any particular generator. And now you need some new math to come into the picture. And this is where we come full circle. We look at these rewrite rules between rewrite rules, and they're called teets transformations. And you can add a generator that's expressed by other generators. You can remove a generator that's expressible by other generators, or add or remove things that are fully redundant, like and just contain no new information at all. Adding a generator is sort of like adding a vertex to like a polygon. Removing a generator is deleting that vertex. Adding a relation is like adding an edge that goes between in your graph two of these vertices. And removing a relation is deleting that edge. So when you do homology theory, you look at these polygons and whatever, you could talk about how they're invariant, things like 2, under adding and removing edges as long as you leave the shape intact. That's exactly what a teets transformation is. It's an abstract way of continuously transforming a space in a very loose sense. So now we know why we need homology theory. All right. Rewrite systems are spaces. We look at ABBD, and we might say it rewrites two ways here. This is a critical pair I've written, right? So we would say those are the vertices, are those, the edges, right? And then if those two are confluent and rewritable to each other, then that fills in a face. So we have vertices, edges, and faces built out of rewrite systems. So we have polygons built out of rewrite systems. So we can do things like add and delete and use all this fancy machinery from homology theory to talk about our rewrite systems. All right. So if we're confluent, we say all cells of a certain shape have to be able to be filled by a 2-cell, which is to say that you should have 0 in one of those spaces of sequences of numbers, right? Because all your loops need to be contractible. So we want to find a homological invariant of a monoid that's preserved under teets transformations. Or more loosely speaking, we want to be able to know whenever we can fill up all our spaces, which is the same as completing all the paths so they all come to the same place. All right, so now I found this much nicer set of explanatory diagrams on chain complexes. It's much more visual, at least. It's from visualizingmath.tumblr.com. I don't know if that's where it's originally from. It was hard to source it. The point is, what we're talking about with the is you have a sequence of things. The things are what we call the various homology H0, H1 of homology at different dimensions of a space. They're related by what we call boundary maps, which is if you have a pyramid, you take just the faces, and that gives you the boundary. If you have a solid triangle, you get the edges. In fact, if you know anything about differential geometry, or even more simply, if it's just multivariate calculus, there's some theorems that involve integrating along boundaries, right? So that notion of a boundary works for these boundary maps too. I'm not going to talk about it. There's a cohomology theory called theorem homology or cohomology, and it lets you prove Stokes' theorem and all the other great facts from these guys. Because the boundaries are the same. That's why the differential operator looks the same, but in an abstract sense. But we're not talking about that sort of space. We're not talking about manifolds. It all works there, but we're not. Solid triangle, boundary maps or edges, so forth. The chain condition is that the boundary of the boundary is 0. And again, in differential calculus or whatever, multivariate, that's something that people might be familiar with. When you have a closed form, you have to go around and 0. Yeah?
Should be mentioned, the reason that works is you're actually counting your things with pluses and minuses. They cancel.
Sorry, yes.
Geometrically it wouldn't make sense.
Right, if you're just adding, going around these things all the same way, obviously it's not 0. The point is, sometimes you're subtracting and sometimes you're adding. It depends if you're going forward or backwards conceptually on a path. And that's where a lot of the hard computation is everyone mixes up their pluses and minuses. So we're going to try to avoid that, but that's what, yes?
Could you explain more about why the non-manifolds?
We're just not talking about them. It worked. The general homology works for
The
them great.
question?
It's just,
Can you repeat?
well, the answer is, why am I not talking about manifolds? And the answer is just because that's a whole other talk. That's the only reason. It's cool, but it's not for here. So now we can look at this. So this is really not too scary. I made it scary before by adding more text around it. It's just a bunch of things that are numbered, a sub n and a sub n minus 1, a sub n minus 2, and a bunch of maps between them. It's just a sequence that keeps going down. Now, if you know what a kernel and an image are, a kernel is sort of the stuff in a function that that if you go across the function lands in 0 or lands at the identity element of a group. And the image is just the place that a function lands. So if you have an image of a function, that's just every possible value that it can emit. And you have something called a quotient of a group we won't talk about. If you quotient the kernel by the image, that gives you this group that we call the homology group, just in general, in almost any homology theory. I know there's exceptions, but that's as a matter of course, that's what you do. So you look at the sequence of functions and you look at if where one lands, and all the places where one lands are all the places that the next one sends to 0. That's what we mean by saying the boundary is 0. And in a sense, it's saying that there's not any weird structure that comes all the way from the top to the bottom. Like you can sort of slice this thing up as you please, and all the information is contained locally. And in fact, therefore, what they describe as long chains are built from small chains, but we're not going to talk about that. So what if they're exactly the same? That's the nicest case, right? And we call that being exact. And an exact sequence is just a chain such that it's exact at every n. And this, again, if we're not talking about manifolds, I'm going to keep making the analogy. When you talk about a form that's closed and exact or closed but not exact, it's similar. So now this is getting, I'm introducing a lot of rough machinery here, right? So bear with me. The resolutions take a while to get to, and I'm jumping to them, because I'm giving you all the tools we need to understand what's going to happen in this paper, or at least in the first version of the paper. So if we only care about this homology structure, this group structure, these numbers and things that are associated to each dimension of a space, we want to treat any two spaces with the same associated groups as equivalent. So a weak equivalence is what we're just going to call is any map between spaces that preserves this stuff in some sense. And it's just a way of loosening things up that you do a lot categorically, is you just want to do everything up to like almost the same. Because like I said, ignoring that there's different presentations, ignoring you can write the elements in different order. So everything sort of just, it's not your normal on-the-nose equality. And a resolution of a space is you pick another space that is basically the same as that space. And then you just give it some extra conditions that make it nicer to work with. That's all a resolution is. It just takes one way of looking at a space to another nicer way of looking at a space for some version of nice. And the way I think of it is you take a space and you rearrange it. So just like one might have a sequence of like images taken from hundreds and hundreds of satellite photos, and then you put them all out on the table, and then you cover them up with each other like the Polaroids, and to reassemble like the whole image, just like they do on like Homeland or whatever, right? You can think of a resolution as maybe, what if I just then chop that up, in a much nicer way after I and did all that rearranging for you. That would be a nice way. It's a bad analogy, but it's close enough. Okay, so a plane object, if you put it as a chain in a complex, it's only going to be at the one level it's at. It's not going to be at any other level. You're just sticking it inside something. So you have a group and a complex is between groups. Well, it's got zeros all over it. But now you can take a resolution, and what you're going to do is you're going to make something that's exact. So it has this nice property where everything fits together perfectly. But now to do that, you've sort of stretched out the object. And the way I think about this is I've taken like a sample in biology of some organism, like some plant, and now I've sort of stretched it out over Petri dish, or maybe like chromatography, right? So I'm looking at all the little bits one by one, and that's what a resolution is going to be of a single object here, is a way of stretching it out so I can look at each of the levels of structure of this object one at a time. And hopefully that's a lot simpler than looking at it all together. And so and that's what a resolution is. So now we have something called, now Squire in 87 finally answered this question I'm getting to. Thank you for bearing with me. Like I said, it's a journey, but it's rewarding. And I hope I'm doing okay keeping you involved here. We have a free ring generated by a monoid, but I wanted to turn that into how you actually think about it if you write these guys down, because that's an abstract description. A concrete description is you write a polynomial equation, right? Just a formula of x plus y plus z or whatever, except instead of x, y, and z, we have the elements of our monoid. And that's all we do. We take the variables, instead of being free variables x, y, and z, to be elements of the monoid, and just have a polynomial equation over them. And in a sense, you call that a formal power series, because it's not a variable. You can't put like 17 into it for a. A is just the element a. But you can just write it like a power series. That's all it is. 5a plus 2b minus 3c, so on. That's the free ring generated by a monoid. A free ZM module over a set. Sorry, I'm not going to tell you what a module is, but I'm going to tell you how you can think about it, again, very hands-on, algebraically, in this special case. And that's, instead of just having A, B, and C, if you have a ZM module over S, you just have pairs of something from M and something from S. So 2AX plus 4CY, AY minus AZ, right? If S has our elements X, Y, Z, and M has our monoids A, B, C. So it's just it's just a polynomial, except instead of your free variables, now you have pairs of the monoid in the set. So again, it's a perfect, and you can manipulate it by the usual rules of algebra. So it's just a formalism. Now you have a presentation of a monoid, and E1 or sigma 1 there is our generators, our generating set. Sigma 2 is our relations. Now I told you what an exact sequence is, right? Remember, it's the thing so that the boundary of the boundary is 0. All the information is local. So Craig Squire, 87, showed if you give me a monoid, then I can always construct this weird homological structure on top of it that I've given you, a free sequence of these ZM modules, or an exact sequence of them, that we would call a partial resolution of the monoid. So I can stretch the monoid out. Like I'm looking at it through on a slide, and I've smeared it onto the slide. And these are the formulae for each of the functions that relate the things so that everything fits together perfectly, like Lego pieces. And they just say what you do at each step. Now, the brackets are weird. I'm going to go on an interlude that you can tune out for if you really are already half lost. I will say the brackets threw me for a loop, and Tom Lawler helped me out a lot. But we'll get to that in a second. The overbar just injects the generator of the monoid into the monoid itself. Yeah? Do we have a question? No? Stretching, okay. So the theorem of Squire is that this sequence is a partial free resolution of length 2 that is composed of what are called finitely generated and projective modules. So that means that M for all monoids is of, quote, homologic with a finite presentation, is of, quote, homological type left FP2, which is a very fancy thing. It sounds much nicer that way. All right, so let's talk about this bracket. In the simple case, like in D1 in the middle, all we're doing is when we're saying it's an element of the module, that just right, so it's a polynomial in these monoid elements, but we're just looking at the single element in it. So how do I tell the monoid element A from A as a trivial polynomial in the module? Well, I put it in brackets. It's just a notational convention. Now, in D2, S of A and T of A are the source and the target of the rewrite relation. And it's the source minus the target is the way that you expand this formula out. So this is just a mathematical formula. You can write it out. But the source and the target aren't elements of the monoid. Or even the generating set of the monoid. They're words, right? Because it's a rewrite between A, B, C, D, Q, right, and BRS, right, or whatever, right? 2 full strings. And we've got to turn those strings back into elements of the module as well. So we use the bracket again, but we give it a different meaning, right? This drove me nuts, because a Haskeller, right, a term should only have one type, and this is using type overloading. So if you're a Java programmer, you'd be much more comfortable with this. Now, right, so all the Java programmers are very happy right now, because they're using function overloading. And we define bracket of this type to send elements from the words. And it's an inductive function. It's a fold. And all it does is it says if you see the unit element, you send that to nothing. And if you see the head is U and then the rest of it is V, then you just take U and then you add the action of U as a module, which I don't multiplied by all the rest of it after you've reduced that as well. So it's a fold. And in fact, you can think of it like Horner's rule for in some sense, for finding the value of a polynomial and evaluating it. And that's all that's doing, is it's evaluating the thing at the monoid in some sense to map it properly. That's enough of an aside. You don't need to understand that. It's just if you do want to read the paper, that drove me nuts, and I want to save you the work. Okay. By the way, this paper is not the paper that I'm talking about tonight. This is another paper. This paper is Squire's theorem, Craig Squire. But the version of it I'm talking about is a paper which I'm going to give a reference to by Malbos, one of the co-authors on the paper, and also Giraud, not Girard, Giraud, who started working on Squire-type problems basically from the time of Squire's theorem. And it's called something like polygraphs and monoids of finite derivation or something. And it basically is a much nicer explanation in modern terms of Squire's results. And so, and it serves as a way to lead into what I'm going to get to. I still have enough time to get to, if I still have enough attention from you. So now we're going to complete Squire's theorem, this beautiful theorem from 1987. If you have a confluent system, it's not just finitely presented, but it's confluent. If you can get this, turn it into this like normalizing normal form procedure, right? If you can take these relations and turn it into something that, just cranks out a normal form, just like we would like, just like Knuth-Bendix is one way to do, then if you have that, you can generate a further thing, right? We only went to sigma 2 before. Now you have a sigma 3. And the sigma 3 are the fillers, those 2 cells in the critical pairs. And so given all of them, you can extend the entire thing up a dimension, and it's still exact. And it's still an exact sequence that is a extended partial resolution of the prior partial resolution. And that is the theorem. And so it's not of homological type left FP2, it's of homological type left FP3, right? So if you've been following along, you see the 2 went to 3 and that went to 3. So you understood that much. All right, good. Now, this is gorgeous. FP is finite and projective, but you have to know what a projective module is, and I'm not telling you, sorry. Okay, every monoid is of type left FP0. Every finitely generated monoid whose generating set is finite is of type left FP1. Every finitely presented monoid, right, which is to say whose generating set is a finite set and whose relations are a finite set is of type left FP2. And every finitely presented convergent monoid is of type left FP3. So here's a sequence of homological invariants that tell us something fundamental about these very computer sciencey objects, these rewrite systems. And he concluded by saying, well, let's just take one example. I just came up with this one. This is some old example. And he says, well, this is some weird example. We define this monoid for everything k. We say if k is greater than 2, then this monoid is not FP3. So it doesn't satisfy this. But we did prove that it does have a decidable word problem. So now, therefore, if k is greater than 2, then sk has a decidable word problem but does not have a finitely uniquely terminating presentation. And that is a very nice theorem. And he had to go through a lot of work and a lot of homology to finally prove that question I started with, right? And so this was a very striking result that used a lot of very fancy math to show something that you would think that wouldn't take that much. And it got people very excited, and they kept working on this for years thereafter. And like I said, Giraud was one of the first, and he came up with a more categorical version of Squire's proof. And they kept trying to extend it to richer theories and richer structures. And but let's take a little breather here, because I know that was a lot. And this is how I felt when I was writing these slides too, believe me, you're not alone. So let's take a meme break. Friendship regained with homology. Homology and rewrite systems both are my best friends. All right. Yeah, do we have a question?
I just want to know, was that system that he was demonstrating that for just an example of something that breaks that and he wanted to prove that, or is that just something he pulled out of thin air and just...
It was because he wanted to provide a counterexample to this famous question. But he doesn't say, I'm going to provide a counterexample. He just says, oh, by the way. So, yeah, that was why he did it, of course. So also in '87, some fellers were working on this stuff. I haven't read this paper. I think if I did, you wouldn't want me to talk about it. I've skimmed it. Okay, but it involves algebraic theories. String rewriting systems present monoids. We want to now talk about term rewriting systems. And what they present are algebraic theories, right? And term rewriting is, of course, much richer. And if when we talk about computer science and compilers, we talk about term rewriting. That was, as with monoids, we often want to look presentation first, but different presentations, again, describe the same object. So, an algebraic theory, I'm going to tell you what an equational theory is first, which is slightly different in the way I'm using the words. Everyone will use these terms slightly differently. So you have operations, but now, right, before you just had like some set. Now we have a set of operations at 0, which is like your A, B, and C, your constants, but at 1. Like negation, unary operations, binary operations, plus, minus, times, all the way up, 3-ary, 4-ary, and universally quantified relations of those operations. So you can see all along we've been using this notion of a theory. When I said there's groups, right? It's got one 0-ary operation, which is the constant for the empty group or the identity group. It's got negation, a 1-ary operation. It's got multiplication, a 2-ary operation, and then those are relations because they're universally quantified. They say for all x, and they give an equation on that. An algebraic theory, in the way I'm talking about it, is an equivalence class of equational theories, which is, again, that different equational theories might present the, quote, same thing. So the real way you talk about what that same thing is something called a Lever theory, and that involves a bunch of category theory, so I'm not going to go there. Instead, I'm just going to say it's there, believe me, and we just want to talk about an equivalence class of them. So again, we talk about string rewriting in computer science. Now, term rewriting. When you have Haskell, you have type classes and laws. Those are theories, right? Like, monoid is a type class in Haskell. That's exactly an algebraic theory. If you look at not just the operations given, but the laws that, the compiler can't check, but you must provide. And there's a lot of examples of that. Algebraic theories as type classes. Even num is really like the poor man's theory of a ring with some weird stuff in there. And there's other examples. Type classes with functional dependencies. also give a rewrite system as such on the top level. Because if you have, A, B such that A implies B, then that's a directed rewrite, that implication, right? And that's why rewriting in logic happens a lot, is implication is a way that you can rewrite things. So when you're solving type class equations with functional dependencies, you're really engaging in rewrite theory. And in fact, there are a couple of questions that were sparked in rewrite theory by people trying to ask if you could actually decide certain type classes, or if maybe you shouldn't allow them. Syntax trees under equivalence induced by eval, for you schemers out there, are a way to think about term rewriting. And eval itself can be thought of as rewriting, right? Evaluation, and you have programming languages that are written entirely through term rewriting. And I'm giving a little warning. Lambda binders with higher order functions mean that there's an important sense in which a theory is not algebraic. So Selinger has a paper about this. I'm not going to explain it. I just want to warn you because it's the first thing you want to do, and it's really cool, but it doesn't quite work. So, and yet Jay's waving his head. It's sort of dumb, but it's not so simple. Let's leave it there. Computer algebra, which is what motivated Knuth-Bendix. You want to, do formal differentiations, solve integrals or something, right? Through computer algebra like Mathematica does. You're rewriting equations. You're simplifying things. It's all rewriting. And of course, theorem proving. So now we're 30 years later. We had these results in '87. Now 30 years later, what happened? Got old. If a homology of monoids lets us prove facts about string rewriting presentations, then what if we can use this stuff about the homology of algebraic theories in that paper I showed you? Can we then prove facts about term rewriting systems as well? Yes, we can. And that's the subject of the actual paper today's talk is around. And so they start off with some very concrete examples. I gave you groups with 5 relations, right, that actually captured all the different elements of associativity. You can reduce them down. In fact, you only need one operation in this one relation, and you think of that as a division. And it's this weird division because you can't fully divide, otherwise you'd have a field and not a group. But you can divide in these weird cases only, and that's equivalent to having a theory of a group. I don't understand it, but it works. Anything that you can present this way we call one-based, because you can give it by one big rule. And those rules can be big. Semi-lattices, distributed lattices, they're not one-based. There's no one rule. Normal lattices, or plain old lattices rather, are one-based. Boolean algebra, the first time, a single axiom, it just only had 40 million symbols, so one rule to rule them all. This was later improved, yes. Okay, so a question people have asked, I actually don't know why they've asked it, is which things can be made one-based. But people have put some work into it. I suppose it's sort of useful. It's a place to start, because at least it lets you say something. And we want to be able to say anything about these systems. Because otherwise, a rewrite system, it's just like a macro system. It's like, you don't have hygiene or anything. Like, what is it? It's just, it just takes something and it turns into something else. How do you have a theory of that? So you just need to at least crank out some results before you can even begin to believe in this thing. Okay. So here's the big idea. If I have a rewrite relation, for example, g of f of x and f of x, right? G is binary, f of x is unary, equals h of x. Well, what is that doing? Well, it's deleting 2 g's, and it's adding back an h, right? That's what it's doing on the level of a diff. So let's just give it that equation, h equals 2f plus g. Let's forget that the g is on the outside and the f is on the inside, right? It could have been f of g or g of f of g, but it's just character. It's deleting some characters and adding some other characters. So this is actually what the paper does, is it takes this crude homology given by these equations, and it says, well, this is enough to already let us say some things. This isn't nothing. Right? I can tell you if I have one axiom that only relates, say, G and H, and another one that only relates E and F, they have no characters in common, so there's no way I can combine them together. Right? So then I need at least 2. Right? So there's some notion there. And in this case, because H equals 2f plus G, maybe I don't need H. Maybe I can always rewrite it into 2f plus G if I'm clever enough. And maybe I can delete one of those rules. Maybe I can delete one of those generators. Anyway, it's a place to start. And it's something that we know how to count, which is letters. And since homology is about counting things and finding cycles of things, let's just start with letters. Now, okay, so that was the easy part. And then, woo, do they hit you with stuff. Oh. Let me tell you what a context is, and then we're going to stop because it gets scary. So in the term we had above, the g of f of x, you draw that out as your little graph, and you can see, well, there's one line coming in, because that g can happen anywhere. And it's just anywhere in your syntax tree that you see a g of f, right, if you see it as an actual abstract syntax tree. Right, but those two f's have to come out to the same x. So I rewrite that to h, that comes to the same x. What if f and j are different things, and they go out to different places? Right, that's x1 and x2, or x and y, two different free variables. And then I rewrite it to h, and that's got to go out to two different places too. But how do I know? But the two aren't the same, so I better make sure that the guy who it goes out to an h corresponds to the right one from this. I better not mix these up. So we need a notion of a context. We need to know, and what that is it's a term with a distinguished variable, as well as all the other variables. And that variable is the whole at that space. It's the place you're going to substitute into first. It's where you're looking at. And that actually does relate slightly to this sort of context as derivative stuff. I couldn't tell you how, but it's clear that there's a relation. And then they create something that drove me nuts trying to figure out, and I couldn't Google it, because nobody else uses this to mean this. They came up with it, I think, in just this paper. And it's a bicontext, which is the context in N and in N. Oh, I miswrote this. That made it even worse. It's a blank. It's an arrow. A context in N and a morphism from a term in M to a term in N, I think. The M's and the N's kept getting confused for me by this point. Bicontext induce functions between the terms. In the other way, yeah, contravariantly, which are rewriting functions. I think if you do it categorically, sorry, for 3 people in the audience, this is actually some sort of not a slight, but a comma category construction, but I didn't want to work it out. I was preventing this because it wouldn't help anyone else here. That's what's going on, is they have a comma category with bicontext. Then they do some other things. Yeah, they move from a monoid to a ringoid. The way they describe a ringoid isn't first order. It involves functors between higher categories. I'm not going to tell you what that is. It's a ring with more than one element, in a sense. That's all I'm going to say with types. They go to the free monoid, to the quotient of the free ringoid, which means that when you look at a context, all I'm going to show you is this one example. Again, now we're sketching it. This is dense stuff. But instead of just G and H and the subtraction we had naively, this box is your empty holes, right? So now we have G if this is the focus, we have G if this is the focus, and F, but you can only have one place for the focus. So you have to quotient by all the different possible places you could first substitute into, right? And that's really what all this machinery is about, is keeping delicate track of which free variables match with which things, so you don't mix things up, right? So it is this crude notion of counting letters, but it's counting letters crudely, combined with counting free variables very carefully. Okay? Now, this looks familiar. Instead of sigma, they're now writing P, but it's the same thing. So P is your theory. Every convergent presentation of an algebraic theory gives rise to a partial resolution of the form. We saw this before. Except now we have R, and R, like I said, is the quotient of a free ringoid by context equivalences, and not this pretty monoid that we had before. So that's scary. R looks scarier. The generators and relations don't look scary. They look the same. Here they're using underscore instead of bracket, which is really irritating because they share an author, so they should have shared notation. And with P1 the generators, P2 the relations, P3 the critical pairs. Okay. Theorem. The rank. I told you, the rank of a group. The rank of the homology group H1, which is the kernel of D0 over the image of D1, is a lower bound on the number of the operations of a theory. In a very crude way, you're counting the minimal number of elements in that group. And that group is a crude approximation of the real structure that you know is only letting you count more things than you can, fill more holes than you can, because you're letting all the operations commute past each other. You've sort of abelionized it, as they say, by letting everything, by forgetting the ordering in which you see the letters.
It's reading the first line. Perhaps, I can't believe it determines. It determines it on one side.
It doesn't determine it. It's a lower bound.
Yeah, okay.
That's what I'm saying. It's a
that's
lower
it.
bound.
Because
It's
there
a-
might be homotopical obstructions that can't be seen. Okay.
I'm not sure. Well, I'm just telling you, it's a lower bound. So if that number, if you get a number out, and that rank is an integer, it's the number of elements in some group. It's a weird group. You count the elements. If that integer is 2, then you know that theory must have at least 2 operations. It might be that it might need at least 17, but you know it's at least 2. It tells you something, but not everything. Martin? The question is why the emphasis on one-based theories. And the theorem is indeed more general. They just started with the question of one-based because that was apparently something people had studied. And they had come up, basically, like I said, 30 years later, they'd gone off for 30 years and invented, higher cohomologies of algebraic theories and non-abelian stuff, which they don't even get into here. And they wanted to write a paper that said, look, I can give you a number that you might be interested in, and this is why that's an interesting paper. And they said, well, people have asked if a theory is one-based, so that's a good question to answer. Let's, let me try to show you that you can do something with this theory. Second theorem. Again, the rank of H2 is a lower bound on the number of relations of a theory. And hence, that gives you the result you want, which is if the rank of H2 is greater than 1, then that theory cannot be one-based. They do have counterexamples. They have things of rank H2 of rank 1 that also cannot be one-based. But it at least lets you find some of them. And that's exactly like Squire. None of these methods are exact, and none of them are what you would call constructive methods in that sense. They provide obstructions. They show you there's more holes than you wanted to get somewhere. That doesn't tell you that you even know how to get somewhere at all, right? But it at least tells you something about why you can't get there from here on occasion. And that, I think, is often but not always characteristics of results in homology. It's certainly characteristic of this set of them. And I'm almost done, actually. I'm making good time, but yeah. Well, no. Well, the question is, can the lower bound be 0? And I think the answer is, I think if it's 0, you'd know, because everything would trivialize. If you had no relations, you'd know. You'd be a free group. If you had no generators, you'd know. Yeah. Okay, that might be true, actually. Yeah. In that case, it's just that their cohomology fails entirely. Yeah. But yeah, so yeah, I think that's the answer. Is it doesn't tell you anything. Okay. So this is an old slogan that people like, and believe me, this is the end. Which this is from 1938, and this is what we did. We topologized and we got some real results, right? And this is from Marshall Stone, and he was introducing Stone duality, which generalizes to Topos theory, among other things. What he was generalizing was point set topology. There's no really catchy slogan for the new process of looking at homotopy and homology and talking about how mathematics is going that way. There's a very extended quote from Yuri Manin that John Baez always likes to quote. It goes on. But he's talking about fundamental psychological changes. This is from an interview in 2009. Instead of sets, you look at spaces. And when you want to return to discrete objects, you actually look at them as continuous components of spaces. And instead of looking at the sets as fundamental, you look at these infinite things. And then he says there's an ongoing reversal in the collective consciousness of mathematics. The right hemisphere and homotopical picture of the world becomes the basic intuition. If you want to get a discrete set, you pass to the set of connected components defined up to homotopy. From the start, Cantor's problems of the infinite recede to the background. From the very start, our images are so infinite that if you want to make something finite out of them, you must divide them by another infinity. And this is true in the homotopy groups. And now I want to close with my own thought, my own TED Talk notion here. See, I was preparing this last night. Just like if you eat ice cream before bed, you get weird dreams. If you read Alexander Grothendieck's Pursuing Stacks before bed, you get weird dreams. Pursuing Stacks. So, I was thinking, as I was preparing this talk, about an image like this one. This is Monet. A meadow. And the sun plays on it, filtering through the leaves. And as the leaves rustle in the wind and the branches move, the shadows move around. And we're looking at those shadows, and there's all sorts of patterns in them. And you can look at them forever. But you can't understand them. No, don't ask the question, I'm being poetic. And then you look up, You look up, and you look at the tree, and you look at the sun as it passes through the leaves, and you see the higher structure, and you understand that the play of the shadows, as beautiful as it is, does have an explanation, but you would never find it just looking at the ground. And that's my motivation for higher structure, is when we look at these Betti numbers, when we look at these rewrite systems, we're looking at the shadows of these beautiful towers and the homotopification of mathematics in a sense. It's maybe not understanding the trees, but it's from the beginning when you walk in, noticing that they're there. All right, thank you. Woo!
If you're able to, within the time constraints, I'm curious as to why lambda terms that are bound to other lambda terms don't constitute an algebraic equivalence.
The answer to why lambda terms aren't an algebraic theory is there's the paper by Selinger I'm going to recommend called "The Lambda Calculus is Algebraic," and he shows his idea of how to fix it. And there's something called zeta, but I think of it as just under eta expansion. And it's if you have two terms x equals y, you want lambda x. Well, sorry, I shouldn't use x for both things. You want lambda some free variable, lambda phi of x to equal lambda phi of y. And you can't capture that in a combinatory algebraic theory fashion. You need some notion of higher rewrite rules. And there are ways, in fact, with higher rewrite systems to maybe get a lot closer, and that's one of the places that higher rewriting as a theory emerges. One thing I should note, actually, while I'm sticking on the higher theme, is all of homology theory is often best thought of, it turns out, I didn't talk about it here, in an infinity categorical context, and these chain complexes themselves are objects in an infinite category of chain complexes. And what that lets you do is take all the higher dimensional information and look at it all at once instead of a piece at a time. And look how it relates all at once. So everywhere you look, there is this process at every step. And in fact, the fact that higher rewrite systems as a topic turns out to mainly have been something that higher category theorists had been studying for years without calling it that, is something that they found very striking. And there's an associated workshop at FSCD on higher dimensional rewriting and applications, and 2/3 of the people there are just N category theorists looking to rebrand. So.
One behind you here.
Yeah, I guess I had a question about kind of the practical applications of this. Well, you mentioned, for example, that this could represent the syntax tree of a language. I was wondering, does this result then tell you that given some syntax tree, there is a way to find a lower bound on the shortest way to represent that, basically?
Well, it's a syntax tree and equational relations, right? So it's rewrite rules that might say all is left associate plus, or maybe factor out the times from something. If you have a times b plus a times c, then it'll be that way or the other way. So you need those equivalences, and you have rewrite rules and equivalences, and it'll tell you a presentation can have at most this many. So it might tell you if you could eliminate, or not if you could eliminate, but if you have obstacles to eliminating terms, or if you have obstacles to eliminating rewrite rules. But in real life, you don't want to have the one 4,000 character rewrite rule that rules them all. You want to have the simple one sometimes. So what I find more elegant here is the fact that I can draw pictures and think of these as tangible objects, my rewrite system. It's not just some weird stuff. It's a shape, it's a space. I can touch it, I can see how it moves. So I don't need just this one result. What I want is this intuition that these things I'm working with have the structure, right? That's why I ended it. That is, I want to look at these things, and even if we don't understand the math in this paper, we can look at the graphs and we can say we can look at the trees, right?
Cool, thanks.
Did you have
I wanted to ask about the word problem. And is this all? Could we see rewrite rules as a specialization of the word problem, and then even there, are we looking at like a higher order?
No, the word problem is just one question you can ask about an equational presentation, which is, does it have decidable equality? It's not necessarily the most interesting question you can ask. There's a lot of interesting things that don't have decidable equality, for example, the real numbers. And of those things that do have decidable equality, well, in a sense, they're all equivalent to some number, right? They all fit in finite memory. So the decidability of the word problem is only one. It's only one basic question you can ask, and in a sense, what you're asking is there anything interesting about this at all? And if the word problem is decidable, there's an sense in which the answer is no. Because you could always then replace all the elements of your thing with just 0, 1, 2 for some n, basically, and be done almost, or maybe all the integers at most. And in fact, and that's why this is interesting. If we're only asking for the cases where the homotopy is 0 or trivial, it wouldn't be that interesting. The whole point is you do have higher structure, you do have loops, and that's where everything interesting happens. That's why the halting problem gives a counterexample, but people still like to work with languages which can embed the halting problem. So maybe that answers it. Yeah.
Yeah, I might be going out a little bit on a limb here, or just have my brain stuck in the matrix algebra of the first talk, but is there a way possibly to relate this to like spectral graph theory and eigenvalues and rank?
I'm sure there is. I'm not the person to talk about. Another approach to group theory, I will say, that a lot of people are find very interesting is groups that you think of as acting on matrices and sort of affine spaces and so on. And I don't know anything about it, and I don't know how it. I know that you can do a lot of homology with that. Mm-hmm. I don't know how much of that has anything to do with how you apply it to algebraic theories.
Right, because I was thinking maybe if you could represent this as like the term rewriting as a linear transformation in a vector space, and potentially have the rank equivalent to some dimensionality, and I don't know, make interesting statements.
Maybe. That's a good question. The answer is I haven't a clue.
Okay, thank you.
But hopefully I've given you a couple tools here so you can read the paper and maybe see if you could do it.
I appreciate it, thank you.
Michael, I think, might actually be able to give an answer.
Very quickly, I'm not entirely sure, but this last speculation sounds like you're about to rediscover Grosvenor basis.
Mm-hmm. All right, so Google Grosvenor basis is the answer, yes.
We have one more question here. We'll do that.
Is there a geometric characterization of confluence?
Well, the characterization of confluence is precisely that all two cells can be filled. Now, to do that, you need a notion of directedness, so there's a little machinery. But yeah, they in the paper, and in particular the polygraphs of finite derivation type, they give a very nice notion, and it really is all two cells of a particular character have fillers. And that's what lets them generate, and that's why you can extend that complex by one more. Is you say, if all two cells have fillers, which is the geometric characterization of confluence full stop, then you can extend your resolution using those fillers. But the converse is not enough, right? If you can extend the resolution, maybe you did it in a way that didn't use the fillers. So, yeah. So it's a one-way relation.
Great. Okay, let's
Thanks for your time.
Thank you
It was a lot of
again.
fun.